Today's speaker doesn't need any introduction. But anyway, it's a great pleasure to introduce Jerzy Zabczyk, and he's going to talk about the Musiela SPDE with Levy noise.
Thank you the organizers for having me here. And Jerzy accepted my proposal to devote the first part of my lecture as an introduction to mathematical finance. The equation I am talking about is related to modeling of the bond market. And I will write the equation, the simplest version of the equation I will write now, because if I run out of time, then nobody would know what the equation looks like. So the equation is in one space variable, psi is non-negative. So this is the simplest version. Then we have the first order derivative, and we have non-linearity, which is non-local. I think it is of, because of this, it is of some interest. So there is a function, a real valued function, if I'm talking about one-dimensional Levy noise, function g prime, then there is an integral term inside, sigma eta or t eta d eta multiplied by sigma psi. This is dt part and plus and here a Levy process. I will go. Can you read it? Is it large enough? So this is a Musiela equation in more or less its simplest form. Z is a Levy process. It was introduced initially when Z was Wiener process, as you can imagine. And so my talk is concerned with extension of some results to the Levy case. So my talk will be divided into three parts. First, derivation. Second, I will formulate some results, but only formulate and comment on existence, positivity, and so on of the comments on the equation. But the new part will be the third part, in which I will discuss the problem of explosions. So the explosions. So it turns out that when this sigma is linear, which is the most desirable case, then in the Wiener case, there was always an explosion. So the motivation for us was to see, okay, if we change to Wiener, to Levy, can we get non-explosive solutions? So first, one. So the stochastic integral enters into the mathematical finance through the concept of capital and portfolio. So let's assume we have a bank account. So S0T is a process of this form, RSDS. R is a rate. So investing £1 in a bank will give us at moment T this amount of money. So this is the, and okay, then we have prices of some commodities. At the moment I am considering only finite market. Let's assume that S1, S2, Sn are prices of some commodities. They could be shares, they could be some bonds, but we can also think that S1T is the price of a gold or a silver. And we now invest in this, in such market. What does it mean? We have an initial capital X. X is initial capital. And we split X into several parts. Namely, we put some amount into the, first of all, I invest P, one moment how I write it, P1 at moment 0. I will buy this amount of the commodity. So I will have S1 0 plus Pn 0 Sn 0, and the rest I put into the bank account. So it is P0 0. So by PT I will describe a sequence of, so in general, PNT is the amount, is the number of commodities one buys at moment T. But at the moment I will consider the situation when the portfolio is constant on the time interval 0 T1. Then at moment T1 I will find, this is called, the sequence is called portfolio. I will change the portfolio. So now what will be the capital at moment T between 0 and T1? Capital will look as follows. I think this amount will give us E, or say I can write S0 T pi 0 plus pi 1. I can write, okay, I will write this way, S1T plus pi 0 and SNT. And the main concept now is that we consider the so-called discounted capital.
So the pi 0, 1 over 0 is the pi 0,
One moment. This is correct. This is. No, one moment. I mixed the notation. So here is time.
What? But it's the initial.
So I don't.
Doesn't super zero mean the initial?
No, one moment. This index is capital N is the number of commodities. So now I would do better if I say that I choose numbers P01, P0N at moment 0, and then at moment T, but between 0 and T1, I have this amount. Okay? So now the discounted amount is Vt divided by S0T. So this is by definition. And it is equal to one moment, I need here yes, well, one moment. What I have here is P00 plus, okay, this is what I have. It is written. So if I divide, I will have S0. Here, this term will disappear, and here I will have by S0T, S0T. So now if I calculate the increase, so I want to find out what is minus what I will get P01 and S1T minus S1 0 plus P0N Sn dash T minus S dash N 0. So I can say that this is the integral. It is a stochastic integral from 0 to t. I have my constant process pi t, pi s, applied to the discounted price process. For t between and T1. So if I think that's the definition, you know, pi s is constant on the interval 0 T1. So therefore, we can say that the discounted price, say the capital, is written in this way. It is a stochastic integral. Now, you can generalize this to piecewise constant strategies. Now, at moment T1, I will not write. You split the capital. You have a capital at moment T1. You split this capital into, say, again, now it will be at moment 1, P1, S1, say, T1, plus P1N Sn T1, and you will put into the bank the amount which is left, and here, so the difference, I denote the difference by P1 0. The assumption is that either I borrow, then this number is negative, but what I really choose, I choose this vector P11, P1n. Now, if you do what I did before and calculate the increase of the capital, then I think for piecewise constant strategies, we will get the same, this formula again. Pi s d ss. Pi is piecewise constant, so we keep strategy constant up to moment t1, then we change it, and on the open from the left interval t1, t2, we keep again a new strategy. But we always observe at moment of changes, we observe the constraints. We either borrow or put on the bank account what remains. So what we really choose is the number of commodities we buy, and then we compensate with the bank account. So if I borrow too much, then I think it will be reflected in the capital. So what? So this is I think the essence or the main relation between stochastic integration and the mathematical finance. Then stochastic integral is really the capital corresponding to an investment policy in commodities. I needed discounted here because I wanted to forget about the bank account, finally. Now here, what I'm choosing only commodities. And the bank is somehow to allow me to borrow. Yes?
Excuse me. So we are explaining in a very pedagogical way the self-financing
yes.
approaches. For me, it's always a little bit a problem to understand if it depends on at which moment exactly I do the rebalancing. So
yes, I think at moment 0 is clear.
Yes, moment 0 is clear. But
now I keep strategy up to moment t1 included. And then, so I could say that I do rebalancing at moment t1, but its effect is visible after moment t1. So to get pi predictable, I think it is left continuous. So somehow pi s was given on this interval, fixed, and then on the open from the left interval, it is the second portfolio. Okay, so stochastic integral is really an important thing. And now we say that, okay, then we generalize this. We say that if pi s is a predictable process, then if it describes, and we take it as a description of a portfolio, then this is the capital, the evolution of the capital. And we say that the strategy pi is arbitrage strategy, but up to now I think we have only mathematics. You know, we don't. I'm using some jargon words, but it's mathematics. So we say that pi is arbitrage strategy if, say, there exists a moment t such that the probability, or say moment that the capital or the integral dss is non-negative for t with probability 1, and with positive probability is positive. The probability, say at moment DSS is greater than, is positive. One has to impose some assumptions on the class of strategies, but the class is reasonable. So, and we say that our market, so it means our system of prices, does not allow arbitrage if we cannot find a strategy, arbitrage strategy. So this is a requirement on the model. And if assume that S is a local martingale, that the discounted bond prices are local martingales, then the stochastic integral will not have this property. Now we cannot have a martingale which starts from 0, which is always non-negative, and then with positive probability is positive. Okay? And so we, so there is a connection with the martingale. So now,
I don't think you want to require the integral to be non-negative for all t. It's enough for it to be non-negative with probability 1 for the final t. Be an arbitrage.
Okay, but I required more. But I think we could, okay, I leave it this way. So now one would like to know when to have conditions under which the market or our system does not allow arbitrage. So we could say, okay, if this is a local martingale, it is okay. So if we require that prices, discounted prices from local martingale, then we know that it will be arbitrage free. But there is a theorem of Delban and Schachermayer, which is a generalization of many earlier results, that the market is arbitrage free if there exists a measure P equivalent to the initial one, such that on a new probability space, this process is a local martingale. But, okay, so this is one thing. now what I wanted to add, that sometimes, and I will do this, we assume from the very beginning that our model is such that the bond prices, that the prices, discounted prices, form a local martingale. Why this assumption is often used, and it is related to the problem of pricing. Pricing contracts. And it is, I think, the second ingredient of the general of the mathematical finance, that assume that a contract gives its owner, say at final moment, that the contract says that at moment capital T, the agent will pay to the owner an amount of money related to the prices of the of some commodities. And the problem is how much one should charge for this. The idea is as follows, that we would like to ask for at moment 0, we would like to charge X. If X is sufficient, if an investor can find a strategy which will recover this amount of money. So it means that X is a number such that there exists a policy, a strategy, such that using this strategy, pi s ds, we can recover what we have to pay. I think or that we can find X such that if we cannot recover exactly, we would like to find X such that this is greater than this amount and X is smaller among all such numbers. So what is important, that this definition is almost sure definition. You know, if because I'm using only almost sure statement. So now, if I take yes, if I divide, one moment, how is it? I divide this by S0t plus, so this was not discounted, but after the division I will get discounted capital, and here I will have psi st divided by S0t. So pricing leads to this equation. So now, if I know that this is a martingale, so I'm working under the martingale measure, I can calculate the expected values on the both sides. Expectation of this part is 0, and we get, say, what I will get? I will get x times the expectation is equal to the expectation of psi st divided by S0t. So this is an important ingredient. We have, to some extent, a formula for x, where x is the price. So the models, to work with models such that the discounted prices are for martingale, because I use martingale here, is useful because it gives you a formula for the price of a contract. Yes. So this is the not yet the derivation, but as far as the general mathematical finance concepts are concerned, I have finished. So if there are questions, so there are, okay. So now I go to a market which is related to the Musiela equation. And this is a bond market. And this market is theoretically an infinite market. So what we have for capital T, this is the price of a bond at moment t small, which at moment capital T gives $1 or £1 or $100 or $1,000. So again, so this is the price of a bond, such that if small t is equal to capital T, it is 1. But when we buy it, it's usually smaller than 1. And I am now explaining his Morton approach to the bond market. So that's the bond price. And for each capital T, usually bonds mature for some t's, capital T's, not for all. We have bonds for some capital T's, but it is theoretically useful to consider that we have bonds for each capital T. So what was the assumption here? That the bond price can be represented as the integral from 0 to t f ts ds with minus. And this process here is called forward rate process. At a given moment t, now, we know the prices of all bonds with all maturities, with all future maturities. So at moment t, we know this function for all capital T. So now, so what does it mean? It means that if if I have one bond today, at moment capital T, I will get 1. So this I know for sure. So what I wanted. So now, if I invest £1 in bonds today, then at moment capital T, I will get Yes. So this is why this function is called forward rate. Because I have £1, I buy some bonds. So this is it has an intuitive meaning. So it means so this is forward rate, and in fact the short rate R t is equal to f tt. If you think that it is like, what is a short rate? It is, you imagine that you buy bonds for a very short period, and then you go with this time to fixed t. Then I think this formula really shows that if capital, that this is the short rate, or it could be accepted as the short rate. So now, in this model, one proposes formulae, so the evolution of the forward rates. So I think this is not important, this is important, and one assumes that for each capital T, this process is an Ito process. So it means it is of the form alpha t dt plus sigma tt, and here I will write dzt, where z is a Levy process. So this is one, say f 0 t. It is, I think I should write this way. F0t is the curve, the forward curve at moment 0. So we have here a random field which varies very much in small t, but as far as capital T is rather smooth. And anyway, so that's the assumption. And to consider this process for all small t, we extend the definition of alpha and sigma by 0. Alpha t is equal to sigma for t greater than capital T. So there is a natural question: under what conditions alpha on alpha and sigma this market, infinite market, is arbitrage free? So what does it mean? We should take discounted prices, and I will say pi if you think a bit, you will realize with those extensions that this is the minus integral from 0 to capital T f ts ds. Say at least. So the short rate disappeared because of this formula here. So the question now is, under what conditions on the model is a local martingale. For each t is a local martingale.
Yeah, if P had the same as P, oh no, sorry, no.
He's different.
Sorry.
So
Sorry, why did you make this comment about t greater than or equal to capital T? What-
I think because here, in this formula, Ts could be greater and could be smaller than T. And if it is smaller, then from those identification, it will be constant to FTT.
Okay.
And now, so how to find conditions under which this is, say, a local martingale. For each S, this is, it's a stochastic integration. You can apply Ito formula. You calculate this by Ito formula, and you, using it, you can find a dt part and the martingale part. And you equate to 0 the dt part. And as a result, you will get the answer. Answer is as follows, that but to give an answer, I have to say something about the Levy process, Z. So I postpone the answer, and Z is a Levy process. Erika introduced it yesterday. So what I will need is that E minus, I will need Laplace transform. One needs Laplace transform. If ZT is a Levy process, then its Laplace transform is of the form E T JZ. It can be infinite. I think this can be infinite, but when it's finite, is equal to JZ, where JZ is a function minus AZ. A is a real 1/2 Q squared Z squared. This part corresponds to the Wiener process. This corresponds to the deterministic drift, plus the integral E minus Zy minus 1 minus Zy characteristic function of y, and measure mu dy. So Q should be non-negative, A is a real. That's the formula, and what we can say that this is finite, so Jz is finite if and only if the integral E minus Zy mu dy is finite. Measure nu and parameters AQ are called characteristics of the Levy process, and measure nu satisfies the condition that if I take of 1 and y squared mu dy, then this should be finite.
So you need some exponential moments.
Yes, you need to, you know, if you need jz for all z, but if you need for positive z, as it will be often here, this will be well defined. Okay, so now the answer is as follows.
So you have no assumption until now.
At the moment, not. And I will not specify precise assumptions under which we have the answer. There are. I will give references to papers. In fact, in 1996, so there was a paper by Bjork and others, and they formulated something similar in a more complicated way. Something similar to what I will write. But then there were many other papers which specified precise conditions. So the answer is that the integral alpha ts ds should be equal to function j calculated at sigma ts ds. I think this is called AJM condition. We could call it in the Levy case. If your process is Wiener, then the function j is this one, and you have the square of this integral should be equal to this one. So what we can say that alpha is determined uniquely in terms of sigma. So differentiating with respect to capital T, this formula, we get that alpha T is equal to the derivative J prime sigma, and then derivative of this, which is. So in fact, requiring that the model is arbitrage free, I should replace alpha by this object.
So in fact, if you understand well, in the framework of Stokes, if you make a model by Levy, you have incompleteness. You have more probability.
Yes.
Probability, but here, in considering all the possible t, then you have.
I will not discuss completeness. There are some. Usually, you will need infinite dimensional noise to get completeness. But in general, you don't know.
Uniqueness, somehow, uniqueness of the probability of.
No, what I am saying is only this, that if I assume that forward prices F are of this form, and I require that the process P hat, this process, is a local martingale, then necessarily I will need that this condition is satisfied.
You're working with a fixed measure.
I'm working with fixed measure or with this with the martingale measure, which I tried to advertise at before, that working with arbitrage free with martingale measure gives us formulae for the prices of some contracts. So maybe I will make a break, or you think?
To you and the chairman.
I can speak long. I could continue, but so maybe let's make 3 minutes.
This is for an hour and a half.
And I will write what we get of the forward first. I will write I pass to the third part of my talk. So I haven't yet derived the Musiela equation, but the rest of I will describe how to derive it, but the third part of my talk consists of discussion of explosions or non-explosions in the case when sigma here is a linear function of f. So I will assume that f, it is a requirement. We want to investigate models in which the so-called volatility is a linear function of the forward rate. This is the simplest so yes, so one assumes that sigma is a deterministic function times the forward rates. If under this requirement lambda is a deterministic function, we will get the following. Here it's better to write t minus f t minus, because in the equation with the Levy noise I should have, usually we put left limits of the solution. So I am assuming that sigma is a deterministic function of f t minus capital T. Then the equation will look in the following way. It is j prime integral from t lambda tu f t minus u du lambda f t capital T dt plus lambda capital dzt, and say small t. So volatility is a linear function of the forward rates. As I said, it was noticed in the PhD paper of Morton it was even 89, something like this, that if Z is a Wiener process, then there is an explosion in this equation. So the model was abandoned, and much more popular became the so-called BGM model, Brace, Gontarek, Musiela model, in which instead of they used different modeling in which they can use linear volatility. I'm not discussing this anymore. So now the third part will be concerned with the problem of existence of non-exploding solutions to this equation. But I need to indicate, so I skip a bit the second part. The second part was supposed to be about Musiela equation, how to get Musiela equation from what I discussed here. So the Musiela idea was as follows. Here the process, this process as a process of capital T with time changes, is evolving in a different set of functions. The definition, capital T should be greater than small t. So his idea was that one replaces all objects by, one replaces t, the time to maturity, by t plus psi. So given small t, given capital T, we introduce psi, and psi is called time to maturity. If you plug alpha into this equation and you do the following changes, that you defined RT psi, it is FT t plus psi, and BT psi is equal to sigma t plus psi, and you use this condition here, the non-arbitrage condition, you will end up with the equation which I wrote at the beginning, but there is no equation here. We will get an equation only if we assume that sigma is a function of f. So this trick is called Musiela parameterization. And it allowed to go to the Markovian situation. And so with this writing, we could, with this definition, we can and sigma t plus psi is equal a function psi of, say, f, yes, f, oh, I can write r t, a functional psi, under appropriate choice of psi, we will arrive at an equation, a similar equation to which I wrote at the beginning. I think the function I took in the first, when I started, that psi was a Nemetsky nonlinearity acting on, so this was a, say, sigma psi r t psi. So we get, so one gets this equation. I will write again, j prime to psi, here will be, say, sigma eta r t eta d eta sigma t plus the dz t. So now we know plus the first derivative, d r, it's this way, this way. So we have an equation, and several people considered problems of existence, uniqueness, existence of invariant measures for this equation, positivity. An important problem, I think, which really motivated the theory was the so-called invariance problem. Namely, you in financial practice, forward curves form usually when estimating them, they form a finite dimensional manifolds of curves. So the problem was to find conditions under which the solution to this equation evolves in a given finite dimensional manifold. You know, with the Markovian formulation, you can you understand better the situation, and so on. So maybe I will mention here Filipovich. I could, for the Brownian motion case, I will mention recent book by Carmona and Techranchi. But also several people worked on the Levy case. This was the Wiener case. Okay, that's we don't have for the Levy processes very strong results on existence of invariant measures. What was used by several people was a generalization of what we had with Giuseppe related to dissipativity method. So this is what is used here. And okay, one has to propose function spaces, in which function spaces to work, and so on. I skip this because I want to discuss, I have 20 minutes to discuss the solution to non-explosion problems here. And I don't go to the Musiela parameterization. There are two reasons. It's more easier at the moment to deal problem in this formulation, and we are writing with my collaborator. We try to translate explosions and non-explosions results which we have here to the Musiela formulation. But I do only this. So I am considering, the problem which I am considering is as follows. Let lambda t be a positive continuous deterministic function. Positive. Say continuous function on the set T, which consists of I am fixing one, say, maximal maturity T star, and I am considering the problem of here is T star, T star. I am looking for a random field, which is, say, F is Cadillac. Cadillac in small t, say continuous in maturities, continuous, properly measurable, and so the field is defined here, and we would like to find conditions under which there exists a solution to this, which is for each omega bounded field. If I so because explosions, I interpret here that I cannot find a process F such that it has those properties. So in particular, for each omega, it should be, say, or for almost all omega should be bounded. So condition, so bound existence of bounded solutions. Some comments at this moment? Now, explosions is something going to plus infinity. For each omega, I don't want a solution to be uniformly bounded, but for also, it's useful to notice that if, so this is set tau, capital, but if I have fixed x and y, I can consider this equation in such sets as well. If you look at the equation is meaningful in each such set. And in fact, what we will show that we can find, in the explosion case, solutions which are, say, bounded on a smaller set, and they explode when the set becomes larger. So, why it is easier to deal with this equation? Because we can rewrite it using Dole and Dat formula. Namely, look dFTT. I can, since because of linearity, I can take lambda outside of everything. I have, I can say not lambda but f. Yes, I can. Okay, so how I can I write the equation? I can write the equation f, and here I will have the drift part, dt part, plus there will be a drift part, lambda t dzt. I'm not writing this part here. It requires time. So this is for each fixed t, this is a nice Levy process, and we can use Dole and Dat formula to write that f tau t is equal to a given quite complicated positive, say, process. No, okay, I will write here f0t. I'm writing the Dole and Dat formula from 0t j prime ts lambda s u fs.
You have linear equation, and the Dole and Dat formula is just a formula for the solution of the linear equation.
Yes.
Is that correct?
That's what it is.
Yes.
And why this has a name?
That's a good question.
No. Try to find the form of the solution in the case of general semi-martingale. If you have here the increment of the general semi-martingale. Even in Protter's book, which is very concise, it takes 1 page. So I think it is a beautiful formula. There are not so many nice formulae as this one. SU du. Then there is lambda st ds plus t dzs, and there are jump parts s smaller than t dzs e minus lambda s t dzs. This is the not Laplacian, this is zs minus the left limit. So from this formula we can deduce, or we can justify considering processes z which such that this number, so the jump times this number plus 1 is positive. We are looking for positive solutions, positivity of solutions implies that we should have DZS say positive. So this requirement can be translated into the terms of measure nu. So we will require that nu has support on an interval minus plus infinity, where this number is the supremum or the infimum of this function lambda. So the equation is considered under, I think this is a natural condition for the equation. If we make this assumption, then we can rewrite the equation. I can use for this stochastic integral with respect to Poissonian measure. In any case, I can write that there will be a process with nice trajectories, and in the exponent we will get integral from 0 to t to s lambda u lambda su f. I should write here left limit of s, but one can also forget it about. It is not necessary, it is equivalent writing. du. Here is lambda s t ds. So there should be s minus left limit, but you can show that equations with minus or without minus are equivalent. So and A is a positive process. We can yes, so finally we get such an equation. So I have 7 minutes, so I will formulate the final answers.
How does the jump perhaps with floating?
Are you asking about the form of the equation, or no, I think jumps are in the function j prime.
Oh, okay.
Function j is here. What you have to do is to calculate derivative, and if those terms are not present, you had only z squared, then the derivative is z, and you would get here without this term. So it is an equation for a non-negative, we are looking non-negative process f, such that it satisfies with probability 1 is bounded on a given time interval.
But still you don't have, the equation still has f on the right hand side, doesn't it?
Yes, I think it is unpleasantly non-linear equation. Even if this is linear, then it is exponent of some integral parts. So first theorem 1, that if there exists a bounded solutions, then necessarily existence of bounded solutions implies that the measure nu, in fact, should be concentrated, nu concentrated on zero plus infinity, and Q should be 0. I think, as I said, now Q non-zero is a Wiener process. So this is a necessary condition. And now, so I assume that nu is concentrated here, Q is 0, and defined the function ux, which is something like the, it's y square nu dy for x non-negative. It is a well-defined function because nu is square integrable around 0. So theorem says assume that ux is of the form x rho and a slowly varying function. L is slowly function on, say, near 0. So it is a, so then if rho is greater than 1, then there exists bounded solution. If rho is smaller than 1, then there are no bounded solutions for positive initial functions and so on. There are no bounded solutions. If rho is 1, under additional conditions, we can get so rho equal 1 partial answers. So this is this theorem follows from a better result, which associates existence and non-existence to the behavior of J prime at infinity. I have no time to formulate this result precisely, but roughly, I think this is next theorem, that if J prime Z grows slower than logarithm, for large Z, then we have bounded solutions. Exist. And if this grows faster than to the third power, then we have explosions. Explosions. In general, function g prime, this is increasing. Under those conditions, it is always increasing. So, as far as explosions are concerned, logarithm appears in the theory of partial differential equations related to explosions. But I finish here.
So there are some equations in more dimension which are of interest, which are related to such model.
No. I think here the spatial variable was time to maturity. And this is one-dimensional object. Maybe in reality, time is more dimensional. But no, psi is, so the equation, say the Musiela equation is on the half line, positive half line.
So your proof is really with respect to the process F and not with the process to R.
Yes. As so if now I go to the Musiela, first I have to specify in which spaces I work. And there are some natural spaces. And as I said, we want to translate those considerations to the Musiela equation, but we have not yet done it. The idea to prove existence is, no, if somebody will ask me, I can discuss the ideas, but I think everybody would have an approach, how to prove existence. You know, if I have an equation like this, a nonlinear one. So for instance, so I'm contradicting myself, but we use the following principle, that, so this is an operator on F. Now, if you can find a constant C such that from this you will know that AF is smaller than C, then you get existence. If there exists C, because you start from 0, you iterate, and your solutions will be always below C. So this is this. Now, how to prove non-existence? You deal with explosive minerals. So you try to, this would take me much time. It is more sophisticated, and in fact, we mimic Morton's idea. If you look into Morton's thesis, it's not for some people comprehensive, but it contains very nice ideas and one can make it precise. So he proposed a minorand, and the minorand was of this type, E x minus t plus y minus capital T. So for t smaller than x and for capital T smaller than y. So the problem is to show that under this condition, if A is sufficiently large, then AF will be estimated by this minorand on a smaller set. But this requires some work, and the generalization was not so completely clear. So the minorand for this and this natural. Okay, we tried instead of C to have a function. No, this would give more flexibility, but we couldn't find. Constants are easier, but if instead of C we take a function with this property, here you have a function and here you have the same function. So you don't get nice conditions. So there is this gap. Here we have logarithm, here is the third power. So it is not so bad.
I still want to come back to R, because if I interpret correctly our paper with you and Szymon, we prove in Gaussian case that R has, there exists some condition for the equation R which has unbounded solutions.
Yes.
And so would it also imply, so it is what you call explosion?
Yes. Here is my answer. That it is related to this term. I think one has to, we will have to assume that this process, the deterministic function lambda, is such that this has Cadillac. Lambda is continuous, but in addition we have to require that this is Cadillac, because it is not always true that with continuous function here this will be Cadillac. And I think what you are referring is to a similar situation with the Wiener process. It is also not true for the Wiener process that with continuous lambda, this integral will be a continuous field. If you assume only lambda continuous, it is not enough.
What, Cadillac as a function of what?
Cadillac as a function of t, small t.
Which t? Big T or?
Small t.
Sorry, but
Why wouldn't that always be Cadillac as a function of small t?
yes, I think your remark concerns the case when you have the t in the kernel, no?
But I think
In
we
Bragg
have,
case.
no, but even, if I have a Wiener process and lambda is only continuous of those two variables, then the integral is not continuous as a function of small t. One moment. No, capital T. No, I'm talking. No, sorry. Capital T. Thank you. It is not capital T as a part.
Basically, you don't have flow, that's what you're saying. Got you.
Yes, and I think the question of Gislav refers to this, that we had to assume something about lambda to know that this is, say, continuous in capital T. Continuous in capital T.
Yeah, is this
Okay, so let's thank Jerzy again.